This lesson is for page 6 through 9 in the matrix packet, and we're going to learn some matrix arithmetic. And here's some properties that describe that if you add two matrices, it doesn't matter what order you add them in, the result is the same, meaning the commutative property for addition holds. The associative property for addition holds, so if you had three matrices and you were adding them together, that it doesn't matter what order you add them or group them, that the sum of the three matrices will be the same. And if you multiply a matrix by a number, then it also doesn't matter kind of what order you do the numbers in the matrix here. So there's three other properties. Keep in mind as you are reading these properties that the capital letters A, B, and C are matrices, and these lowercase letters are what are called scalars or real numbers. So capital A, B, C are matrices, and K and H are numbers. So here, like in this example, 4 times A means to just take the matrix A and multiply it by the number 4, and that is just defined to be 4 times 3, 1, 5, negative 2, 0, 6. Notice that the matrix has these corners on here. If you just use vertical lines, that means to find the determinant, but when you put these corners on, then that is describing this as a matrix. So I am multiplying this whole matrix by 4. I should put that 4 kind of more like this, and it just takes every term in the matrix and multiplies it by 4, so that this becomes 12, 4, 20, negative 8, 0, 24. Kind of just what you would expect. And so 1/3 of C would be 9, 0, negative 3, 6. If we take 1/3 of that, then this will be 3, 0, negative 1, 2. And if I did 3 times A minus 2 times B, you could pause and try this on your own, but that would just be 3 times 3, 1, 5, negative 2, 0, 6, and 2 times B, which is 4, 1, 0, 8, 1, negative 3. So first I'll do the multiplication. 9, 3, 15, negative 6, 0, 18. And 2 times 4 is 8, 2, 0, and 16, 2, negative 6. Now, we haven't added or subtracted two matrices. In order to do that, the matrices need to be the exact same size, and so then you just end up subtracting or adding each term according to the sign there. So this term subtracts with this term. 9 minus 8 is 1. 3 minus 2 is 1. 15 minus 0 is 15. Negative 6 minus 16 is negative 22. 0 minus 2 is negative 2. And 18 minus a negative 6 is 24. Alright, so that's some basics of some arithmetic for matrices. And now we're going to move on to multiplying, which is significantly more difficult than addition and subtraction. So unlike the straightforward definition for adding two matrices, the definition for multiplying two matrices is not what we might expect. And so in preparation for that, we are going to learn how to deal with just a row vector times multiplied by a column vector. So there's a definition here, and let's just go ahead and try the example to see how it works. So if I were going to take and find the product of matrix R times matrix C, then I would take R, which has one row, and C, which has one column, and I'm going to multiply those. And the way that that works is that I get just a single term out of this, and it is equal to 3 times 3 plus negative 5 times 4 plus 2 times negative 5. 9 plus negative 20 plus negative 10. That's not 3 different terms, that is actually one term. So negative 30 combined with 9 is negative 21. So when you multiply a matrix that is one row by 3 columns, and then you take another one that is one column, 3 rows by one column, you end up getting a matrix out that is 1 by 1. So these inner ones end up having to be the same, and the outer ones give you the dimension of your new matrix. And here you can see this is the definition, that if you had a row vector or a row matrix, R1, R2, R3, and a column, C1, C2, C3, that the product of those two matrices ends up being row 1, column 1, plus row 2, column 2, plus row 3, column 3, etc. And those all add up and give you one number. So let's see what happens as we move on and learn how to multiply more challenging matrices. So notice that right off that this matrix is 2 rows by 3 columns, and this one is 3 rows by 4 columns. And so what's going to happen when I multiply those together is I'm only allowed to do it because these 3's are both the same, and then the end result is I'm going to get a matrix that is 2 by 4. It's good to know what to expect out of it. Alright, so when I take these two and multiply them, A, B, I'm going to get a matrix that is 2 by 4, and actually I might need a little more space than that to show it out. When I get this first row and first column, I get that by multiplying the row here by the column here and multiplying and adding each term of them. So that's 2 times 2 is 4 plus 16 plus negative 24. No, sorry, messed that up. Sorry, 4 by 16 and 4 plus 16 plus 3. And then to get row 1, column 2, I will use row 1 and column 2 and do the same thing. 10, 32, and negative 1. And to get row 3, row 1, column 3, I'll use row 1 and column 3. 2 plus 0 plus 2. And to get row 1, column 4, I'll use row 1 and column 4, 8 plus 24 plus 1. Alright, then to get this next row, it's row 2, column 1. I'll use row 2 and column 1. So that'll be 10 plus 32 plus 0. And then row 2, column 2, I'll use row 2 and column 2, 25, 64, and 0. And then I'll use row 2, column 3, 5, 0, 0. And row 2, column 4, 20 plus 48 plus 0. So that matrix represents the product of A and B. And then I just add all these up. That'll be 23, 41, 4, 33, 42, 89, 5, and 68. So this matrix is the product of A times B. So here's just some more practice of multiplying matrices. I'll go ahead and work them out, but you should pause the video and try it on your own. So if I have 2, 1, 3, 1, negative 1, 0, multiplied by 1, 2, 3, 0, 1, 2. Notice that this is 3, 2 rows, 2 by 3, and this one is 3 by 2, and so I know to expect a 2 by 2 when I'm done. The inners are the same and the outers are going to be the result. So I'm going to end up with 4 spots here in my 2 by 2 matrix. To get this first one, row 1, column 1, I will use row 1, column 1. So that'll be 2 plus 2 plus 9. So 2 plus 2 plus 9 is 13. To get row 1, column 2, row 1, column 2 is 0 plus 1 plus 6, that's 7. To get row 2, column 1, I'll do 1 minus 2 plus 0. And to get row 2, column 2, 0 minus 1, 0. So that's what I get if I multiply A times B. Interestingly, if I do B times A, so 1, 0, 2, 1, 3, 2 by 2, 1, 3, 1, negative 1, 0. This time my result here, this is a 3 by 2, 3 rows, 2 columns. This is a 2 row, 3 column. And so my end result is going to be a 3 by 3. The inners have to be the same and the outside will be the resulting matrix. I can get row 1, column 1 by multiplying row 1 times column 1. So 2 plus 0, row 1, column 2 will be 1 times 0. 1 plus 0 times negative 1. And then row 1, column 3 will be 3 plus 0. Row 2, column 1, 4 plus 1. Row 2, column 2 is 2 minus 1. Row 2, column 3 is 6 minus 0. last one. Row 3, column 1, 6 plus 2. 3 minus 2. And 9 plus 0. Notice these are definitely not the same. So the order of multiplication makes a difference in the result. Obviously they're even different sizes, but they're definitely not the same values. All right. Here is more practice of multiplying matrices. In this case, they're 2 by 2s. So if I take 2, 1, 0, 4 and multiply that by negative 3, 1, 1, 2, you should pause and try this yourself. Row 1, column 1 will be negative 6 plus 1 is negative 5. 2 plus 2 is 4. 0 plus 4 is 4. And 0 plus 8 is 8. So that's what I get if I multiply A times B, but if I multiply B times A, even though they are the same size, so I'm definitely going to get another 2 by 2 out of this, the order is still going to make a difference. So here it will be row 1 times column 1, negative 6 plus 0, and negative 3 plus 4, 2 plus 0, and 1 plus 8. So the point of this example here was just to emphasize that the order of multiplication definitely makes a difference. One other thing before we finish this lesson is just the introduction of the concept of something called the identity matrix. The identity matrix for a 2 by 2 is this, and the identity matrix for a 3 by 3 is this. It's kind of the neutral multiplier. So the point of it is, and it's always a square, the identity matrix has to be square, so that it's either 2 by 2, 3 by 3, 4 by 4, 5 by 5. But it's like the number 1 in multiplication of normal numbers. And it just means that if you take, say, a matrix A, that's dimension is 2 by 3 here, negative 1, 2, 0, 0, 1, 3, and I want to multiply it by something neutral, then since this is 2 rows by 3 columns, then this would have to be 3 by something, and if it's the identity matrix, then it has to be 3 by 3. So 1, 0, 0, 0, 1, 0, 0, 0, 1. And what will happen is I will get a 2 by 3 matrix out of it. And because I'm multiplying this by the identity matrix, something interesting will happen. Negative 1 times 1 is negative 1. 2 times 0 is 0. And 0 times 0 is 0. So I just get negative 1. And then to get row 1, column 2, I'll use row 1, column 2. So 0, 2, 0. And row 3, column 3 will be 0, 0, 0. And now row 2, column 1, 0, 0, 0. Row 2, column 2, 0, 1, 0. Row 2, column 3, 0, 0, 3. So the thing to note here is that taking this original matrix A and multiplying it by the identity matrix gets me the same matrix back. So this is neutral. Does not change the value of it. And it doesn't matter if you have the identity matrix first and then you say multiply it by, say, matrix B here, which is 3, 2, 4, 6, 5, 2. This is a 2 by 2, and this is a, oh, I did the wrong one, sorry. Grr. Couldn't work because this was a 3 by 2 and this was a 2 by 2, so this has to be a 2 by something when I go to multiply it. So it's by A, I2 times A. So if you wrote A in here, -1, 2, 0, 0, 1, 3, and if you went through the steps of multiplying the 2 by 2 identity matrix multiplied by the 2 by 3 normal matrix, the identity matrix will keep everything the same, and the result will be, you could confirm that by doing the multiplication. And the same thing will happen here if you take this 3 rows, 2 columns, 3, 2, 4, 6, 5, 2, and multiply it by 1, 0, 0, 1. It won't change anything. The end result will be 3, 2, 4, 6, 5, 2. And we could check that. That would be row 3 plus 0 is 3, then 0 plus 2 gives me 2, and so on. Alright, so that is what an identity matrix is, and when showing that you multiply something by its identity matrix, that it comes out to be the exact same thing. So we will learn how to find something called the inverse of the matrix in the next lesson. Thanks for watching.